In this video, we're going to continue our discussion of pullbacks by proving the following theorem, which says that pullbacks are actually a nice property because they preserve a lot of morphism properties. That is, more specifically, the following morphism properties are stable under pullback: Monic morphisms, right-invertible morphisms, isomorphisms, and equalizers. Now, what does it mean for a morphism property to be stable under pullback? Well, if we remind ourselves what a pullback is in this graphic here on the right, we can see that we have a diagram D with two colliding morphisms, F1 and F2, and we have the triple P, P1, P2, which represents a cone over D, and not only a cone, but it's a limit, a terminal cone over this diagram D. So, if this is the case, then we say that P1 is the pullback of F1, and P2 is the pullback of F2. So what it means is that if, for example, F1 were to be monic, then P1 would also need to be monic, right? P1 is the pullback of F1, and F1 has this property, and that property is stable under pullback. So that means even when you look at the pullback instead of the morphism itself, it still has that property. As I mentioned in the start of the video, you can also state this result by saying that the pullback preserves that morphism property. So either the property is stable under pullback or pullback preserves the morphism property that you're interested in. We'll prove each result one by one, and we'll start by saying that this one is actually already done, and that's because we proved it in the original video on pullbacks. So if any of the terminology is unfamiliar, or if you want to remind yourself of the proof of the first one, then just go check out the original video on pullbacks, and otherwise we'll start with number 2. So let's suppose that F1 is right-invertible. So that means F1 has some sort of inverse on the right, maybe call it F1 inverse on the right. A little too many superscripts and subscripts, but that's okay. So if that's the case, then notice that we now have this morphism that we can chain together, F2 followed by the inverse of F1, the right inverse. So we can actually show that the triple B, the identity morphism on B, and that morphism that we just talked about, so the right inverse of F1 after F2 is actually a cone over D. Why is that? Well, if you want, you can pause the video here and answer that question, because in order to be a cone over D, the two morphisms in our triple need to make these two morphisms here commute, right? This is the diagram D, it has these two morphisms in it, and in order for something to be a cone, it needs to sort of complete that commutativity square for this type of diagram. So we'd need to have that F2 after 1b would need to be equal to F1 after F1 right inverse after F2, right? This morphism after this morphism needs to be the same as this morphism after this morphism. And so does that make sense in terms of the diagram? Well, it does, right? Because we apply 1b here and then we go to F2, or we start with F2, then we take the right inverse up to A and then take F1 back to C here. And so these do end up both at C. And is this the case that this is equal? Well, it is, because if we look at this side, F1 after F1 right inverse after F2, well, this, of course, is just 1A, right? We're just doing the inverse. And that is going to be equal to F2, which is obviously going to be the same as F2 after 1B. So pretty easy to see that this is actually the case. And so we do actually have this cone over D here. But if this is a cone over D, then we have a pullback over D, which is also a limit over D. And that means that we need to have our unique mediating morphism going from this cone to the limit, right? That's what it means for this to be a limit. There needs to be a mediating morphism, theta, going from the vertex of our cone B to the vertex of the limit, or the pullback P. And it needs to be such that P1 after theta is equal to 1B, right? This leg here needs to be factored through by theta. And similarly, P2 after theta needs to be equal to this leg here. So right inverse of F1 after F2. Well, by the first equation, P1 is right-invertible, right? Its right inverse is theta. So we have that theta is therefore the right inverse of P1. And therefore P1 is right-invertible. So that's QED for the first result. Moving on to number 3 in our list. Number 3 says the pullback of an isomorphism is an isomorphism. So this time, instead of only supposing that F1 is right-invertible, we're going to suppose it's an isomorphism. That is, it's invertible on both the left and the right. And if that's the case, then we have some morphism, just F1 inverse this time, which acts as the inverse on both the left and the right to F1. Well, let's just make a couple observations based on that. The first is that based on number 2, we can already say that P1 is right-invertible. So that is, there is some P1 inverse on the right. And why is that? Well, because F1 is an isomorphism, so it's right-invertible. And we saw that right-invertible morphisms are stable under pullback. So this is a pullback for our right-invertible morphism, so it must have some right inverse. But based on that, we can also say that the inverse of F1 after F2 has to be equal to P2 after the right inverse of P1. So that is the inverse of F1 after F2, so this chain here, actually has to be equal to this chain here, the right inverse of P1 and then P2. And why is that? Well, that's a great exercise. So pause the video here and prove it should just be a couple lines why this equation is the case. And the reason is that we have this commutativity square here, the original one that created our pullback diagram. And so if that's the case, we have that F2 after P1 is equal to F1 after P2, right? That's just our regular commutativity square for the pullback. And then now we can just start applying the inverses that we have. So we can apply on the left, both sides, F1 inverse to get F1 inverse after F2 after P1 is equal to P2. And then we can apply our P1 inverse on the right to both sides of this equation to get F1 inverse after F2 equals P2 after the right inverse of P1. So we'll keep those two facts in mind, and we'll continue by applying a trick that, as we've mentioned before, is a very common pattern that you'll see in category theory, which is we take some sort of definition and we apply that definition to itself viewed in some other way. So that's a bit of an abstract way of thinking, but let's just look at what I mean. So let's look at this pullback P, P1, P2, and let's remember that because it's a terminal cone, it's also just a regular cone, right? It is a limit, so it's a terminal cone, but we can just think of this triple P, P1, P2 as a cone over D. And if that's the case, then we know that there needs to be a mediating morphism, just like any other cone. It doesn't matter that it's the same cone as the limit itself, but it's a cone, so there needs to be some mediating morphism, maybe call it rho, going from our vertex, in this case P, to the vertex of the limit, the pullback P. And it needs to be such that you can factor these legs through rho by saying that P1 after rho needs to be equal to P1, and P2 after rho needs to be equal to P2. But based on these equations, we know immediately what rho needs to be, right? Rho needs to be equal to 1p. Right? Because clearly P1 after 1p is going to be P1, and P2 after 1p is going to be equal to P2, right? That's basically the definition of 1p. So the identity on P is going to be rho. And why is this important? Why is this significant? Why did we pull this little trick of sort of using the pullback as just a cone and then applying the definition of the pullback to that cone? And we established this, but we didn't just establish this. We established that that was the unique morphism that did it, right? So the important part here is that there can only be one morphism that exists that commutes these two properties here, and that unique morphism is 1p. So anytime we find a morphism that satisfies both of these equations, that morphism must be the identity morphism on P. But notice that if we try the right inverse of P1 after P1, but this time put it on the left side of P1, let's try applying that to these equations. So let's replace rho with this instead. So that would be P1 after inverse on the right of P1 after P1 is equal to, well, obviously we can rearrange these because composition is associative. So we get, this is on the right now, after P1. And so this just becomes 1p. And we get that this is equal to P1. So, okay, this here satisfies the first equation. Now, does it satisfy the second equation? So that is P2 after the right inverse of P1 after P1. Well, we know that this is associative again, so we can break up the parentheses, and this we saw here is actually equal to the inverse of F1 after F2. So let's replace these two with the inverse of f1 after f2. And then we need to follow that, or precede that, I guess, by p1. And then we can use our regular commutativity square for the pullback again. So we see that here we have f2 after p1, f2 after p1, and that's equal to f1 after p2. So we can replace with f inverse of f1 after, so now it would be f1 after p2, right? f1 after p2. But this again just collapses to, this time, 1a. And so we have that this is equal to just p2. Right? 1a after p2 is just p2. And so, since this block here satisfies both of these equations here, and we know that any morphism which satisfies these two equations must be equal to the identity on P, we have that 1P is also equal to the right inverse of P1 after P1. But that means that the right inverse of P1 is also a left inverse, right? Because now here it's applied on the left and it's still giving us the identity morphism on P. So we have that P1 is invertible both on the left and on the right, because we already know that it's right invertible. And so we have that it's an isomorphism. And so this equation here gives us QED for number 3. So we have one more property to show in order to complete the proof of the theorem, and that is that the pullback of an equalizer morphism is an equalizer morphism. So suppose that AF1 is an equalizer over a new diagram D'. So we've added this diagram D', and in order to be an equalizer, the diagram needs to have two parallel morphisms. So we have E1 and E2 here. And we're going to suppose that AF1, this pair here, is an equalizer over this diagram D'. So we see that F1 constitutes the equalizer morphism in our equalizer, right? We have an object and a morphism. So F1 is the equalizer morphism. And so we need to show that P1 must also be an equalizer morphism. So P1 is the pullback of F1, and so we need to show that P1 must also be an equalizer morphism. So what would it possibly equalize if we just even look at this diagram and what an equalizer needs? So an equalizer needs two parallel morphisms coming out of the codomain of P1. So if P1 were to be an equalizer morphism, which would mean we would need to have P1 be equalizer over some diagram, well, it would probably have to be this morphism here and this morphism here, right? Those are the only parallel morphisms I can see coming out of B anywhere in this graphic. So it would be an equalizer over the diagram containing E1 after F2 and E2 after F2. So the question is this true? Is PP1 an equalizer over this diagram consisting of these two parallel morphisms? So that's this diagram here with these two morphisms, E1 after F2 and E2 after F2. So let's check. For this to be an equalizer, it needs to be a limit, which means it needs to be a cone. So we need to have the commutativity property that all of the morphisms in the diagram commute with the equalizer morphism. So we need to have, in this case, E1 after F2 after P1 needs to be equal to E2 after F2 after P1, right? That's the first property, which shows that the equalizer commutes with all of the morphisms in the diagram. But we're good there because we have E1 after F2 after P1 is equal to, well, we can use the commutativity square from the pullback, right? So we have F2 after P1, which is here, and we can replace that once again, we've done that a few times already, with F1 after P2. So we have E1 after F1 after P2. And we have that F1 is an equalizer over this diagram here. And so that property means that E1 after F1 needs to be the same as E2 after F1. And that's still after P2. And then we can just re-replace the commutativity square to get back our original composition morphism here. And so we can just say that F1 after P2, which is this, is still E2 after F2 after P1. And that's exactly the result that we needed here. So we're good on the first result. So we've shown that we have a cone, but we need to show that that cone P1 is actually a terminal cone or a limit, or in this case, an equalizer. And so in order to do that, we need to say that if we find some other x and morphism x going from that x into B, which also equalizes these two morphisms, this one here and this one in our diagram. So that looks like this, E1 after F2 after x equals E2 after F2 after x. Then we need to show that there's a unique mediating morphism that goes from x into P, right? Such that this triangle commutes. And if that's always the case, then we have a terminal cone. So let's try to show that. We can kind of look at this equation in a different way, which is to say that it's actually F2 after x equalizing E1 and E2, right? So if we look at it that way, then we can actually say, well, then we have a cone over D prime, right? Our original sort of equalizer diagram here. So we have that x F2 after x is a cone over D prime. And if that's the case, then we have a unique morphism, maybe call it rho, going from x into A, such that F1 after rho is equal to F2 after x. So that is, we have to have some morphism rho here going from x to A, and it goes from x to A such that F1 after rho, so this is rho here, is the same as F2 after x. So this commutes with this here. But that commutativity property is exactly what we need for a cone over D, our original diagram for a pullback, right? We need it to complete this commutativity square with F1 and F2 in it. And that's exactly what it does. So what we get is that X rho is actually a cone over D. But if we have a cone over D, then we need to have a unique mediating morphism going from that cone to our pullback P, right? That's the definition of a pullback. So we have this cone over D, which means that in turn, there must be some unique, say, theta going from X into P such that both P1 after theta equals X and P2 after theta equals rho, right? So those are the two commutativity properties. So if we draw that here, then our theta goes from this X to our P. So this is theta here. And we have that X is equal to theta and then P1. And in the same way, rho is equal to theta and then P2. So it commutes with these two legs here. And if that's the case, then notice that we already have the property that we need for the equalizer, right? We needed a unique mediating morphism that made this equation true. However, the problem is that there isn't a unique morphism that only makes this true. There's a unique mediating morphism that makes both of these true. So the one last thing we need to do to complete the proof is to show that there's a unique one just for this equation. And the way we're going to do that is we're basically just going to show that this equation actually implies this equation. So if you have a theta that satisfies this equation, it automatically already satisfies this equation, and therefore it must be unique even just for this equation alone, because it implies this one immediately. And the way that we can do that is we can notice that we have the commutativity square that we were looking at earlier. So maybe I'll write this in red. So we have the commutativity square, which is that F2 after P1 is equal to, so F2 after P1 is equal to F1 after P2. And so we can follow both sides by theta, right? Or sorry, precede both sides by theta. So we can have F2 after P1 after theta is equal to F1 after P2 after theta, right? I just took the commutativity square for the pullback and I added precede by theta on both sides. And then if that's the case, we know that P1 after theta, according to this, is equal to X. So this gives us that F2 after X is equal to F1 after P2 after theta. But this implies that because F2 after X, according to this equation here, is equal to F1 after rho, we can replace this side by F1 after rho is equal to F1 after P2 after theta. But remember that all equalizer morphisms are monic and therefore left cancelable, and so we can cancel on the left F1 on both sides since F1 is an equalizer morphism, and so we end up with rho equals P2 after theta, which is exactly this equation. And so that shows that if I go by assuming this equation at the start, I can end up right away at this equation here. And so it would not be possible for us to have multiple equations that satisfy this one and not satisfy this one. And so therefore, this mediating morphism is unique even just for this equation alone. And we have that PP1 satisfies the universal property and the commutativity property. Therefore, it is a limit over this diagram with two parallel morphisms in it. Therefore, it is an equalizer. And so this statement is not a question mark, it's a check mark. This is true. And that gives us QED, right? Because we have that P1 is an equalizer morphism when F1 is an equalizer morphism. And so that completes the last part of the theorem, and so we've completed the proof. We'll conclude with a couple exercises. So the exercise is to prove whether or not pullbacks necessarily preserve epic morphisms and whether pullbacks necessarily preserve left-invertible morphisms. So if you want, pause the video here and attempt those proofs. If not, we can continue and I'll provide a couple quick hints. So the answer for both of them is no, they don't necessarily always get preserved. And so in order to prove that, you need to provide a counterexample, so you can construct a counterexample for both. But remember that left-invertible implies epic. So if you can construct an example that's left-invertible and isn't preserved via pullback, then you've already proved the first one as well.